Human language is endlessly fluid. It is a sprawling, unstructured system of symbols and sounds that we use to compress our infinite, chaotic thoughts into a medium others can understand. But that fluidity creates an immediate barrier when we try to teach a machine to read. Artificial intelligence models do not read text. They are purely mathematical engines. They require structured numerical arrays to function, and raw language is deeply incompatible with that architecture. The incompatibility comes down to three factors. Human text varies wildly in length, it is statistically uneven, and it is highly ambiguous. A single word like blinker could represent a person's name, or it could represent a car part. The machine has no inherent way to resolve that context. To bridge this gap, engineers rely on a specific architecture, the natural language processing pipeline. This is a multi-step sequence that breaks the text down, maps it to fixed concepts, and outputs a continuous numerical vector. Translating open-ended human expression into bounded mathematical tensors is the foundational prerequisite for any artificial intelligence system to process, analyze, and reason about language. Before we can begin converting words into numbers, we have to define the statistical reality of how humans actually use those words. This plots word frequency in a standard dataset. While statistical modeling prefers a normal distribution, human language follows a power law, specifically Zipf's law, where frequency is inversely proportional to rank. This creates a long tail. A few words appear thousands of times, but nearly 50% of all unique words appear exactly one time. Because a machine learning model requires a fixed, predefined vocabulary size, this long tail presents a serious problem. If a word is too rare, it gets stripped out and replaced with a generic unknown token, entirely erasing its specific meaning from the data. Conversely, if engineers simply expand the vocabulary to encompass every single rare word, the model will overfit. It will attempt to memorize rare, one-off patterns that offer no predictive value when it evaluates new data. This extreme statistical unevenness forces developers to abandon the concept of using whole words as the base unit. Instead, the pipeline requires a mathematical middle ground for segmenting language. That segmentation process is called tokenization. It is the method of slicing a continuous string of raw text into smaller, discrete computational units called tokens. Simply splitting a sentence every time there is a space does not work. Different languages have edge cases that break this logic, from combined contractions in English to massive compound nouns in German that contain multiple independent ideas within a single unbroken string. The modern solution is byte-pair encoding. It initially treats text as individual characters. The algorithm scans for the most frequent symbol pairs and creates a rule to merge them into a single token. It then iterates, recursively merging the next most frequent pairs to build larger, recognizable subunits. BPE strikes the necessary balance. It allows the model to perfectly map highly common words as single tokens for efficiency, while retaining the flexibility to mathematically process entirely unseen words by breaking them into known subparts. Once the text is segmented into a fixed list of token IDs, the pipeline must project those integers into a real-valued vector space. We call this feature mapping. Historically, one-hot encoding sized the vector exactly to the total vocabulary. Every token is assigned a unique position, marked by a 1, with all other dimensions set to 0. But in a 50,000-word vocabulary, this creates a massive sparse array. Worse, it assumes every word is mathematically equidistant, treating all tokens as completely unrelated. To process full sentences, engineers developed the bag of words model, a method used to compress multiple one-hot vectors into a single, unified document-level representation. Bag of words aggregates the binary presence of the tokens. It checks which words exist in the text and flips their corresponding dimensions to 1. In doing so, it intentionally discards all grammar, syntax, and word order. While bag of words succeeds in creating a computable numerical input, it results in a bloated, brittle system that treats language as a disconnected pile of IDs, rather than a coherent thought. If you upgrade that model to count word frequencies rather than just their binary presence, you immediately encounter another mathematical flaw. High-frequency stop words like the or is will completely overpower the signal of rare, highly meaningful words. To correct this imbalance, engineers utilized term frequency inverse document frequency, or TF-IDF. The first half, term frequency, logarithmically scales down massive raw repetition counts. The second half, inverse document frequency, mathematically zeroes out ubiquitous words that appear in every document, heavily boosting the signal of unique discriminative topics. TF-IDF was the pinnacle of human-engineered feature mapping. It proved that raw counts must be mathematically weighted to be useful. But even with precise scaling, the model still had no way to know what the words actually meant. The ultimate failure of these sparse vector models is that they cannot capture synonymy. A rigid matrix looks at the words car and automobile and sees two entirely unrelated variables. Over the last decade, the field shifted to representation learning via dense vectors, or word embeddings. Instead of massive, empty arrays, words are projected into a compressed, multidimensional geometric space, where related concepts are physically clustered together. Instead of humans manually engineering the features, dense vectors abandon manual feature engineering, forcing the neural network to mathematically deduce a word's essence during training, based entirely on the context of the words surrounding it. The architecture designed to learn this context is called word-to-vec, which relies on two primary models, continuous bag of words and skipgram. Word-to-vec uses a sliding window over the text. In a skipgram model, the network takes a single target word, like agriculture, and attempts to predict the surrounding context words. To optimize, it calculates a dot product score between vectors. As it learns to predict correct context, the score rises, physically pushing the geometry of related words closer together. Word2Vec proved that the mathematical meaning of a word can be entirely defined by the company it keeps. It successfully converted human semantics into pure geometry. This complete architectural pipeline bridges the translation gap. Raw text enters a tokenizer, fragments into optimally sized subunits, maps to integer IDs, and finally projects into a dense, continuous matrix that a neural network can process. Natural language processing evolved from humans attempting to write rigid, sparse rules to building neural architectures that automatically learn fluid, dense representations. Transforming text into this dense format provides the necessary inputs for the three primary structural levels of natural language understanding. It enables sentence classification, allowing the model to analyze a vast sequence of vectors and assign it a single overarching label, like positive or negative sentiment. This same structural grounding supports sequence labeling and structure prediction, giving the model the ability to evaluate individual vectors to determine specific parts of speech, or to map an entire sentence into a hierarchical relational tree. By mathematically freeing the ambiguity and frequency challenges of human vocabulary, we have enabled machines to parse our strings and reason about our world.